All right. Thank you, everyone, for having me, and I'm very happy to be here. I'll speak about the cyber resilient emergency response system, specifically about integrating digital twins and zero trust architecture and reinforcement learning. I'm Monty Abbas from Virginia Tech. The work is in collaboration with CT Lu, also at Virginia Tech, and Azim Iskandarian at VCU. What I'm going to talk about is the give the problem context first, emergency vehicle preemption, how it controls basically critical right of way. At traffic lights, when you have an emergency vehicle coming in, they issue a call to the traffic signal so that the signal can give it preference for the green, so that it can go through. And most of the time, those vehicles will have patients who are in critical need of arriving at the hospital very quickly. We worry about attack vectors in terms of spoofing, denial of service, GPS manipulation, and replay attacks, and so on. So if bad actors are issuing false emergency vehicle calls, they are going to basically stifle the system. And then that impact is going to propagate across the network. So in terms of queues, spillback, stability, and so on. And those of you who have seen the Italian Job movie that came a long time ago would see that, when the bad actors come in, have green everywhere, so the traffic is stuck, so that they can only move around. And then the existing defenses right now, they assume trust, so that whenever that a preemption call comes to the traffic light deals with it as if it's true, and therefore that is fundamentally vulnerable, and that's why we wanted to do this work. So cyber attack on traffic signals, it can have delayed emergency response at the very least. This is not just an ID risk, it's a real-time public safety risk. And then the current systems cannot distinguish the legitimate versus the spoofed EVP request. So our framework looks like what you see in front of you here, the Z-Tracks. It's a zero trust reinforcement learning for anti-cyber spoofing. So the input you have traffic data. This is the normal traffic data that you will get. So vehicle detection from everywhere. In case of the connected automated vehicles, then we have RSUs and OBUs and so on. All of this technology that is getting the location and direction and heading and speed and acceleration from vehicles as they are moving around. And then you have the EVP request. So the traffic is receiving those from the emergency vehicle, and also vehicle GPS and sensors that could be integrated in the system. So all of that is an input. And then if we skip the reinforcement learning module and go and the zero trust policy engine, we go all the way to the signal control, without the work that we'll be doing here, then you have all the input coming directly to the signal control, assuming full trust. But what we are having is a reinforcement learning module that is going to sit in the middle. It is getting the input data, getting the state data from that, and give a trust score for whatever data that comes in. And the zero trust policy engine is going to either allow that, deny it, or flag it for further analysis and enforcing decisions. So that will be the reinforcement learning loop over here. So ultimately, what the traffic signal is going to get is only the trusted data that it should be dealing with. The focus of what I'm going to talk about today, quickly basically, is the digital twin simulation environment that we are using for this purpose. So that's going to be used for training and testing for virtual traffic network. The key gap that we have currently is that no continuous verification of EVP request, and that any rules that they exist, we have them as a static rules. So the detection is going to fail. We're going to fail under adaptive attackers. No integration of cybersecurity with traffic control decisions, and then lack of system level closed loop defense. So the objective, develop the adaptive real-time cyber physical defense, integrate the zero trust architecture, embed the reinforcement learning for dynamic trust inference, and then maintain operational efficiency while ensuring security. The core innovation is that this is the first integration of the zero trust reinforcement learning in traffic signal control, specifically for the reinforcement learning. So all the previous work that we have done was basically focused on the digital twin, and all the reinforcement learning was, done offline and so on, and that's what we are bringing in now in this project. The dynamic trust scoring instead of the binary authentication. So this is an ongoing work right now. And the closed loop system in terms of the detection, decision, and then control, having all of it in real time. That's also something that we're doing right now. And it is designed for evolving adversarial environment. So the Z-Tracks framework, basically the input traffic states, EVB request, and vehicle trajectories. And then for the reinforcement learning agent, the way that we are designing it is to learn from the context-aware trust score. So basically detecting anomalies. And that's a key point that we wanted to emphasize in the work as well. So that's not just the spoofing that it is going to detect, but it is basically verifying that the trajectories that are being received at the traffic signals um, are as expected, given the underlying traffic flow models that are being also obtained from the data and that are being developed in real time. So if for example, if you have an emergency vehicle call coming in at the traffic light and then coming in 5 seconds later before the next traffic light, we know that's impossible to happen given the existing congestion, for example, on the network. So there is that analysis and comparison with the patterns that are being happening at the whole network. And the zero trust engine is basically to enforce and allow, deny, flag decisions, and so on. The output is a direct control of the signal operation. And then we're doing high fidelity digital twin environment. So the digital twin is developed in logic. This is the initial digital twin that we had. Over here, we have only 3 traffic lights, but currently this is being expanded to mimic a VDOT case. What basically the digital twin is giving you, you have traffic is moving. The red cars here are simulating the spoofed emergency vehicles. And then they have their input, they have their output, so origin destination on the traffic network itself. And then what you would see over here is this is a time in the system for the westbound vehicles, time in the system for all the vehicles, time in the system for the side street, time in the system for emergency vehicles, and time in the system for the eastbound vehicles. And this way we're looking at the distribution so that we can see how that system impact all the traffic. And then we have the attack frequency being put over here, and then we are basically simulating it. So the digital twin role it's an agent-based simulation, so we're doing it with any logic. We might expand it to Sumo depending on the needs of the VDOT network. And then it replicates real Virginia traffic corridors, enable safe testing under attack scenarios, and support baseline, attack, and defended comparisons. And then it can bridge the research to the deployment directly. The experimental design that I will show for the initial work was the scenario 1, distributed denial of service cyber attack. So basically, if we have real emergency vehicles coming through, we have the normal traffic coming through, and then we have the spoofed attacks. The second scenario is also doing the same as scenario 1, but having connected automated vehicles. So in this case, the surrounding traffic is aware of the spoofed emergency vehicles, but it thinks that they are true. So in the first scenario, the traffic is oblivious to it. They don't know. It's only the traffic signal that knows about them. In the second scenario, CAVs are also affected. And then the third scenario is if when we apply the zero trust, what is going to happen? So basically, if we take all the spoofed vehicles out, we want to compare the performance of the system so that we know which systems we need to actually implement the tracks on it being most effective. The metrics that we use are the EV delay, the throughput, the Q spillbacks, and the cyber metrics are the precision, recall, false positives. So in the first scenario, that what you see here is a attack frequency of 800 spoofed emergency vehicles. And then basically what you are seeing is this is a time in the system for the westbound vehicle and so on. They are short in the system, the time in the system right now, but that's only because the vehicles don't even make it through. So we are only counting the time in the system after the vehicle leaves. And the total cars exiting is only 326 in this case. So we know that the attackers would have completely blocked the system, and nothing is going to go through as much. And it even gets worse if we have a CAV that are aware of those spoofed emergency vehicle, but they think that they are real, so that their behavior is being changed in the system as well. So in this case, the cars exited are even less, 266, so the system is really blocked. And then if we have a very simple mitigation for the cyber attacks here, basically saying that I'm going to ignore all the emergency vehicles, but that's really, you could be giving them preferential treatment in that case just for the phases that they are on. So if they are going all the way through, basically giving more green for the through phases, but without giving them a one-by-one preferential treatment as they go through. You will see that in that case, the car exited R 1459. So the congestion is removed, as you can also see in front of you here. But that's basically just building the case that if we do it this way, then that is going to be beneficial to the system. So the outcomes would have reduced emergency vehicle delay under attack, restored network stability and throughput, improved detection accuracy, and then demonstrated resilience under adaptive threats, which could secure transportation critical infrastructure and would be with direct alignment with VDOT cyber resiliency priorities, and then also transferable to CAVs and adaptive signal and potentially rail crossings too, because the rail crossing is using preemption as well. And then this is going to be a foundation for NSF, CPS, SATC, and federal scaling. So the current ongoing work, the VDOT application, expanding that case study to a VDOT application with real data and EVB logs and creating feasible cyber attack scenarios. So we're not gonna cyber attack the system, but we're going to think about what would a hacker do, what would a bad actor do, and where would they be most effective so that we can counter it. And then the application of the real reinforcement learning in real time was a zero trust application framework, is a digital twin and producing data sets. And then integration with also CAV systems, the smart corridors and ITS platform, and interoperable cyber physical security ecosystem. So that's where we are right now. We still have about half a year to go. And this work was supported by the Commonwealth Cyber Initiative. And we are very thankful for that. And then as a side note, I guess one thing that can come out of this is to do the Italian Job, the third installment of the movie as a sequel to it. But that's, I can only dream, right? So that's where we're thinking right now. Thank you so much.
Thank you very much, Monty. The last slide was quite creative, I have to say. I suspect some AI there. Thank you very much. There are several questions I can think of. We will keep them for the end. So thank you for keeping the time as well, I have to say. We can move to our second speaker then. Please, again, note your questions so that we can have a discussion at the end. So let me introduce you to Stephen Wolthusen from Royal Holloway, University of London, who is going to be talking about abstraction in critical infrastructures considered dangerous. Stephen, we can see.
Yes,
okay, thank you for sharing.
you.
Yes, please take it from here.
Sound is okay as well. So Yes, I have a couple more slides than we're going to need. It depends on whether we share the slides afterwards. There might be a bit more, but let me see how close I can keep to time. So, I wasn't sure of how much general introductions to critical infrastructure we need. There is quite a bit of distinction between the stability of power systems in the UK versus the US. Apologies to our Japanese colleagues. I just couldn't find the numbers for the Japanese power system because it's a bit more complicated as far as I'm aware. So in the UK, we have about 0.4 outages per year, about half an hour. The US is a bit higher. Again, there's some great variations across the width of the country, of course. And most of that is without active attacks in place. Now, what is quite obviously happening here is that the power system is undergoing a much more rapid transformation than what we've seen over the past 100 years, partly driven by extreme demands for data centers, etc., and partly also, of course, by the integration of renewable energy, battery storage, and so on. And also on the demand side, things like electric vehicles. So compared to where we were just a decade ago, we cannot operate these networks without real-time sensing, decision-making. So 10, 20 years ago, it might have been possible to do some things manually. That's just not the case anymore. And in some sense, this represents probably the most complex critical infrastructure that we have, because at least in Europe, we have a continental scale system that needs to be operating, where the UK is a bit of an appendix to that, but it's still at least somewhat integrated. Now, I'm not going to discuss attack vectors. I'm just taking it as read that for all we know from open source as well as not so open sources, this is one of the main foci of state actors. And we do see that there's actually quite a bit of a crowd going on in our power systems when it comes to state actors penetrating these systems. And with a few exceptions like nuclear generators, they cannot be completely air-gapped, so the pathways exist. Now, one area that we are particularly worried about in this context is not just the safe operation of the power system, that we actually have power, but also that when things go wrong, the assumption had traditionally been that you have something called a safety instrumentation system, which protects the equipment from damage to itself as well as to life and limb of users. And that is no longer really a given, so we cannot really assume that. If you haven't heard of safety instrumentation systems, effectively, normally in a control system, you want to be in sort of the green part of this when you're running regular control. The safety instrumentation system is more or less the last regular backstop that exists before physical damage occurs. And without getting into too much detail here, you really don't want to get to the point where you have to call, I don't know, fire brigade or emergency response teams to clean up the mess that you might have left. Now, why are we worried about these things? Here's an example that may not have made it into the mainstream press. So around Christmas time last year, some of our old friends, the Sandworm team from the Russian Federation, penetrated into a distributed systems operator into Poland. And they came in by way of a remote management platform. And they had targeted deliberately to the distribution network systems. Thankfully, they did not try to do anything too novel. So the attack was possible to be detected, and at some point it could be stopped. But clearly, the same people are capable of doing a lot more. Why they were doing only fairly straightforward and out of service attacks, we don't know. But this could have gone a lot more further down the line, because at this point you could have a cascading effect across a larger part of the European networks. Now, what did they target? Well, they targeted IEDs, intelligent, not improvised explosive devices. They targeted intelligent electronic devices. in this case from Hitachi, also some software elements. This is interesting because the same group, that's what we know from open source intelligence also, they have an entire toolkit in place that allows them to not just brick them like they did here, but to implant functionality, including implants that would affect the safety systems on these systems. So in other words, this is subject to real world attacks. It's not just a hypothetical. Now, let me very briefly talk about digital substations as of one element of this power system. Most of Europe now is using either 6150 or predecessor standard 6870 for running substations. There's a rapid evolution happening, again, because of the needs of the power systems. And what all that does, without getting into too much detail here, is, again, you're massively increasing the attack surface. Right? Distribution networks used to be fairly simple-minded, relatively straightforward, and without much of the way of bidirectional control. That has to change. Now, why is this interesting? Well, because you need to integrate lots of real-time measurements, real-time actuation, and a lot of that is now controlled remotely. And that opens up the attack surface. And what has changed is, let's say, if you look over the evolution of these systems, is that if I can draw your attention here to the bottom right corner of the drawing, is that when this got started, maybe 10, 15 years ago, you still had equipment at the process level hardwired into what's called the bay level, if you remember that from the previous slide. That had the advantage that if there was a problem with one of the, for example, sensors or actuators, it would not affect other elements of the entire processing chain. So in our research, we've mostly focused here on the lower level, the real-time level systems. We're kind of ignoring the higher level elements where you deal with conventional SCADA elements, so just for the sake of keeping things into perspective. But what has changed now is that the setup that you see here is expensive. It requires manual wiring. There's a lot more effort involved. So over time, you have efforts to concentrate equipment into simpler networks that run on what is effectively here, in this case, merging units. And ultimately, so if I just go here to the current state of the art, onto what is ultimately a industrial Ethernet type network, where all of the equipment is sitting on a network. Now, it would be rather poor form to run a single network for critical systems. So in reality, what you see here as the process bus is not just a bus, but it has to provide additional redundancy measures so that a single fault cannot take the entire network offline. In order to support that, you now suddenly have to have an entire chain of standards that need to be complied with in order to provide an adequate level of service. So specifically here, although it's not mandatory, it is highly desirable. You need to have something called HSR, high availability seamless redundancy, and or PRP. And they in turn require the presence of other mechanisms, for example, precision time protocol, PTP, like you've seen a couple of slides ago. And that's where some of the problems are arising, which offer themselves to an attacker. So one of the ways in which such attacks can occur, just again by way of illustration, is supply chain attacks. So you've seen sort of the entry points in the example that I gave earlier. Sort of remote control access mechanism is one way, but even if that were to be configured correctly, we've seen many cases also, again, this is an example from the telecom sector, where recently a lot of UK telco operators got subverted for well over a year before anyone actually noticed that the subversion had taken place. So I'm hoping that I'm motivating here that you should assume that adversaries are in your network. This is just a healthy assumption to be made. And in the case here, it might be that you have open source products, you might have CI/CD components. And I mean, just as a point of reference, I have nothing against Siemens. I work with these guys quite a lot, right? But when you look at the current generation of Siemens industrial equipment, they no longer use a proprietary operating system. Their industrial control systems are effectively a Debian installation that runs the real-time component inside the virtual machine, which means they become vulnerable to a lot of these types of attacks that we're describing here. Now, so what's our job? Our job has been to try and model some of the more complex attacks that can occur in this, particularly in the interactions between protocols, where an attacker might be resident in a system and then launch a stealthy but targeted attacks against a particular system. Now, and you might argue, but isn't there a security mechanism? Isn't there a set of security functions in place? And the answer is yes, but 62351-5 and -6 talk about communication protocol security. So they assume that the endpoints are secure and they're not really paying much attention to the network. If I go here, if I can disrupt the network function, that is a good example of an attack that can severely degrade the functionality, not just in out of service, right, but also attacks that disrupt the functionality of the protocol itself. To give you sort of a short illustration of how messy this is, I don't have much time, so I have to do a bit of hand waving how this actually works. The simple bus that you've seen in the previous diagram, which also the standard kind of assumes is in place, is actually the picture that you see here on the right, because all of the equipment needs to be doubly attached so that a single fault in a network cabling, for example, does not disrupt the entire system. And that's true for the power sector, but it's also true, obviously, for other safety critical systems such as avionics and so on. And in order to keep those systems synchronized, they need to be also disciplined by other protocols, here precision time protocol, which is demonstrated here, so at the top, in this case with an external master clock and so on. So one of the insights that we have is that, well, yes, for a lot of these attacks, the exact topology matters. And at the same time, since we're talking about the distributed system, we need to be able to reason over the state not only of the electronic components, but also the state of the physical system. What are we using for this? And this is where I have to be probably quite brief. Again, there are more slides and papers for anyone interested. What we are using is a variant of the pi calculus that Robin Milner introduced back in the 90s, and that's been used in a number of different settings, mostly for understanding traditional crypto protocols. We have to extend this gently with a type of term algebra to reason over the state of the physical system, because that's not part of the normal setup. And that allows us to explicitly include security targets such as physical system state into the reasoning process, as well as of the more natural representations of things like topologies and so on. So we can validate whether an attack might occur in a particular configuration of a network or is more prevalent elsewhere, but mostly we can only reason whether a particular attack is possible or not. So you don't get quantitative information based on this. That you would have to do separately in, for example, a simulation setup. Now, why is this a particular headache in this type of environment? Well, unlike just about any other network protocol that you might be familiar with, because you're dealing with a hard real-time system, the protocols used in power systems are not able to support the type of acknowledgement that you are familiar with from other types of networks. Because the response times required are so short that by the time you had sent a message and sent an acknowledgement or sent a request for retransmission, the deadline would have passed. So what you get instead is something really strange. It's a transmission where anytime there's a state change that happens, for example, when a sensor detects that something is wrong, it will send the message, oh, something has happened, and it will send a burst, and it will just hope that one of those messages gets through. There is no acknowledgement mechanism in there. And that is a nice example of a possible attack vector that almost writes itself. Right? So if you're able to not just disrupt, but if you're able to degrade the performance of the communication channel, you can change the semantics of the operation right up to inducing behavior that would be harmful to the equipment itself. Now, the technique, and I don't have time to get into the actual presentation of this, so I will skip over this, but let me just very briefly describe how we approach this. One of the key tools that we're able to use in the process calculus that we're using here, in the process algebra, is that we are able to use different types of either, well, very simple so-called structure congruences, but more frequently we're using bisimulation, which is somewhat weaker than what you might be used to see from cryptographic protocol analysis, where typically we are reasoning over traces. Now, in a distributed system with physical elements, you can't really reason over traces because you do not have a global trace, and some of the inputs are just invisible. So what this allows us to do is, for weaker forms of biosimulation, is to group certain activities together and to say that maybe we cannot observe this or that variable, but we can observe some of the outcomes. And as long as the outcomes are equivalent, we deem the protocol runs to be equivalent. There's quite a lot of work that has been going on here over the last 10, 20 years. And it's not just in critical infrastructure, in cyber physical systems. There's also work going on in protocol analysis. But we find it a very useful tool here to be adapted to this particular environment. So as I said, we don't have time to get into the details here. I'll skip that up. Obviously, I'll share the slides. But so long story short, we are able to incorporate what I mentioned on the previous slide, that there is some unobservable behavior, like latency introduced, and we can show whether that alteration of the behavior has a detrimental effect or not. Now, in the example that I had to skip over here, we were actually able to demonstrate in a very straightforward way that an attacker that is able to simply delay the forwarding of some of the messages by a relatively small amount can change the behavior in a way that is compliant with a standard. So you wouldn't necessarily catch that during acceptance testing, but it would be able to affect the outcomes that you see during actual operation of the system. And I hope you'll agree that that's a rather unpleasant finding. Now, this gets even more nasty when you have decisions, for example, by safety instrumentation systems, where if I can induce slightly different behavior in the regular control system and in the safety instrumentation systems, you might have a disagreement between the two. And consequently, the operator doesn't really know what the correct course of action is going to be. Now, this is just sort of a a small example. The main use case that we are studying here is for, let's say, sophisticated attacks that you might expect from a reasonably clever state-based actor. So, of course, there are many more simple types of attacks that you can also consider, but we have plenty of evidence that there may, for example, be implants in critical infrastructures that are dormant for a long time, just waiting to be triggered under, for example, the right circumstances. Now, what we're trying to do is we're trying to identify particularly areas where you have multiple protocols interacting. Doesn't have to be just Goose. We've also published similar work for study in the 5G or 3GPP authentication protocol setup. There are fiddly interactions that are difficult to model, where quite often the standards are written in a slightly loose way that allows attacks to occur. And we're hoping to extend this through, for example, some simulations, and of course also to extend this to other protocols. Right, I think I've more or less kept to time. I have to finish with a slight sort of additional acknowledgement. So some of this work was funded by a grant from Ofgem, and earlier work on which this is based was funded by another part of the US government. As I said, I'm happy to share slides, and hopefully we've motivated that sometimes just using formal methods is the right thing to avoid more obvious faults. And that's not AI, that's a real switch without in this case. Thank you.
All right. Okay. Thank you, Stephen. Yeah, a lot of questions and a lot of additional worries. Not that we didn't have enough already, of course. But thank you very much. I have noted down my questions, so I hope everybody has done the same. So let's move to the third talk for today, and let me introduce Takao Kondo and Shintaro Ishihara. We are moving eastwards from the US to the UK and now to Japan. So the title of the presentation is Towards Resilient Industrial Control Systems Utilizing Penetration Testing Technology. Takao-san, Shintaro-san, to you. Thank
Okay.
you.
Hello and good morning and good evening, everyone. This is Takao Kondo from Japan. Today, actually, we have two speakers, including me. The other speaker is Dr. Shintaro Ishihara, so from Control System Security Center, Japan. So today we are talking about the topic of towards resilient industrial control system utilizing penetration testing technology. So actually, I am an associate professor of the Hokkaido University and the project associate professor of the Keio University. And also, I and Dr. Ishihara have a kind of the affiliations of the Industrial Control System Center of Excellence, IPA Japan. So this is a kind of the institutions of the for training the operators, the actual operators of the companies for industrial control systems. So actually, so we have a kind of the professions of the industrial control system things about this institutions activities. Okay, so let me move on the kind of the our Keio universities and the Hokkaido universities brief research portfolios of the cybersecurity issues. Actually, so we are going to focus on the industrial IoT or control system things, but we have broad research topics, not only the control system things, but also data-driven side cybersecurity issues like analyzing network traffics, open source intelligences. So yeah, such kind of things. Just a brief summaries of the data-driven side researches. We are combining various kind of the data sets, net flow, BGP routing informations, open source intelligence, and so on. Such kind of activities is also very important thing of our research teams. But today's main theme is, as you know, so yeah, industrial IoT or control system things. This is a kind of the research activities of the cybersecurity issues for emerging technologies. The emerging technologies is not only limited to the control system sense, but also spanning the other technologies like 5G or beyond 5G or the future mobile core networks, edge computing infrastructures, and also including AI systems things. Such kind of the emerging technologies would be very important, and the secure system design and implementation is necessary for making robust and sustainable the emerging systems. And yes, one of the big issues is as you know, so yeah, industrial control system things. And as I said at the beginning, so we are focusing on the kind of the penetration testing technologies for the control systems or industrial IoT systems. Okay, so let me move on the concrete description about the penetration testing research and research activities covered by our research team. This slide shows the specific research portfolio in K universities. So we have a kind of the two kinds of the center of excellences. The one is the Cybersecurity Research Center, which is mainly funded by the private sector companies, and the other is there's a cybersecurity project, which is mainly funded by the public sector, like Japanese government things. So the right Center of Excellence, the digital cybersecurity project is focusing on the specific industrial IoT or industrial control system security thing, focusing on penetration testing technologies. So let me wrap up kind of the future or the future of the operational technology, OT. So the operational technology, OT, is a kind of the general term for the technologies for controlling and operating physical systems and equipment. So there are several figures. One is the left one is actually the left one is controlling the a kind of the power generations plant systems in the electronic companies, and the right figure would be kind of the factory automation thing for making automobile things. So such kind of the controlling and automating of the factories and the processes and the is a very important functions for the operational technology, OT. And recently we witnessed kind of the various kinds of the cyber attacks targeting for the OT systems, like ransomware infection at Nagoya port in Japan. So at this incident, so the Nagoya port shut down 3 days, and very high impact for the society in Japan at that time. And the other example would be kind of the supply chain attacks in Kojima industry which is kind of the subsidiary company of the Toyota Motor Corporation groups. So at such incident, Toyota Motor Corporation Group lost at the most $375 million due to the plant shutdowns caused by the cybersecurity incident at this subsidiary companies. So the cybersecurity in OT environment is very important thing at the current situation. This slide shows kind of the awareness or the kind of the futures of the OT security issues. Three kind of the futures or descriptions about the awareness things. The first one is OT systems has a kind of the long-term life cycles. In some cases, maybe so several decades would be the life cycles, very long-term life cycles. So such feature makes fundamental security measures in OT system would be very difficult to implement. This is the first feature for the OT security thing. And the second one is a kind of the expanding the attack surfaces of the OT systems. So this is mainly caused by the kind of the DX, digital transformations things. So which means so OT systems often connect to the IT systems like this figure. So this is a very famous figure originated by the Purdue University, and this is a kind of the typical OT and OT with OT systems connected to the IT systems models called Purdue model. So as I said, the attack surface where OT systems exposes is expanding at the current situation. And the last feature is OT systems are often mission critical. So kind of the proactive security measurement like penetration testing or vulnerability scanning would be difficult because such kind of the proactive scanning activities may cause kind of the misfunctions of the practical OT systems. So we are focusing on the kind of the resilient issues in the our research activities, which means so as I said, the kind of the implementing the how to say so the security measures to resolve the kind of the vulnerabilities, for examples, would be difficult for the actual OT systems. So we are necessary to consider about the resilience things. So the cyber resilience would be composed of the two subcomponents, withstanding and recovery. So these ideas were originated by the NIST special publications. So the withstanding would be kind of the ability to detect kind of the abnormal situations rapidly, so to prevent from declining the performance of the OT systems. And the recovery is the kind of the ability to recover the performance rapidly. So the recovery is based on the kind of the the declining of the performance, but the rapid recovery is the main theme of the recovery, cyber resilience metrics of the recovery. So these two kind of the metrics or subcomponent is very important to realize the cyber resilience. So the situation is the same, not only the IT system, but also OT systems. So we are building kind of the cyber resilience things or framework for the OT systems by adapting the penetration testing technology at the OT systems. So this figure shows the kind of the brief architectures for the penetration testing framework or platforms we are building. There is a kind of the simulators platform or infrastructures to make several kinds of the simulators like a power system, power or electronical system or factory automation thing or communication systems. Each of the simulator would be implemented on the simulator infrastructures. So for each simulators, we are adapting kind of the attack scenarios, which was each of which was made by the kind of the actual configuration information of the OT systems. And then so we after adapting the attack scenario at the simulated OT systems. So we are conducting cyber resilience evaluations focusing on the withstanding and recovery, two kinds of the metrics. And then so continuous kind of the adapting of these processes would be realized by our penetration testing infrastructure. So this figure shows kind of the brief directions to make each simulator called different systems of the actual OT systems. We have two approaches. The one is top-down approach based on interviews of the actual configurations, informations with critical infrastructure companies, operators. And the other approach is bottom-up one, so which is utilizing kind of the actual hardware test bed. So specifically in control system security centers. So here's electronical substations simulated or pseudo plant in CSSC control system security center to make kind of the different systems on our simulator. So let me switch the speaker from me to Ishihara-san about the introductions of the CSSC's pseudo plant systems. Okay, Ishihara-san.
Okay. Now let me talk about introduction of control system security center. And as a note, this slide was prepared for this session, and the official version was created several years ago and may contain outdated information. First, I would like to share a bit about who am I. I'm Shintaro Ishihara, and I'm a researcher in CSSC and a CEO in Cineware, and an instructor in ICSCOE in IPA. And my recent research interests are ICS cybersecurity, network security, and AI security. And now let me explain what Abbas Center is about. And CSS is a Japanese Technology Research Association established to promote collaborative R&D in industrial control systems cybersecurity among multiple organizations. It is approved by the Ministry of Economy, Trade, and Industry, and is acting research and development partnership. And here is the association's member. The association consists of Japanese ICS vendors, ICS asset owners, and operators, and universities. For example, as Japanese ICS vendors, there are Omron, and Toshiba, Mitsubishi, Hitachi, and so on. And as universities, there are Tohoku University and Keio University. And then I explain our objectives and activities. The center is dedicated to the following objectives. One is building technical knowledge in ICS cybersecurity. And second is enhancing collaborative efforts among member organizations in ICS cybersecurity. And last is securing the ICS in industrial user companies through collaboration with vendors. To achieve them, the center conducts the following activities. One is the research and development of cybersecurity technologies for ICS. Second is evaluation and certification of ICS and control devices. And third is education, training, and awareness raising in ICS cybersecurity. And to support these activities with realistic ICS environments, the center maintains a test bed. The test bed includes several types of simulated industrial plants. These test beds cover most major OT sectors, including manufacturing, building automation, process industries, and electronic power systems. And this is a list of our simulated industrial plants. Building automation system, factory automation system, gas processing plant, electric power substation, and chemical process automation system. I will now introduce our plants. The first is building automation system. The BA plant simulates selected functions of building automation systems, such as air conditioning control and lighting control. Next is factory automation system. The FA plant simulates part of material handling in automotive manufacturing, in which the robotic arm automatically sort parts. In this plant, white parts are routed to process A, while black parts are routed to process B. And next is factory automation system 2. This plant simulates part of an automotive assembly process. A robotic arm picks up parts and places them on the pallet. The pallet is then transported by belt conveyor, and the parts and the pallet undergo a laser marking process, which is simulated using LED lighting. Next is gas processing plant. And this plant simulates a gas pressure control process that maintains the pressure in a gas tank at a constant level. The actual gas tank is located behind the display panel, although it is not visible in the photo. And here is the electric power substation. This plant simulates the operation of an electric power substation. Operators can remotely switch between two transmission lines from a control center. And last is chemical process automation system. The PA plant simulates a water level control process. The plant consists of 3 water tanks, and the water level in the middle tank is kept constant. Finally, I explain.
Sorry, can you wrap up, please? Because we're running out of time.
This slide is last slide.
All right, okay.
Finally, I explain activities with our test bed. In training, we raise awareness of ICS cybersecurity through demonstration using our test beds, and we provide hands-on exercise for detecting and defending against simulated cyber attack using the test bed. And research is here. And finally, an in-use case by members organization is here. One is technical working session, demonstrations for customers, and the validation of research and development results. And this is collaboration with Kondo Sensei is one of these validation. This is the end of my talk.
Okay, thank you very much. That's all from the Japanese team.
Thank you very much. Arigato gozaimasu. So if you can stop sharing the screen, we can move to the questions. There are already some questions in the chat. Okay, so I guess this is from Arief Iswanto. Question 1, I suppose this is for Monty. Would you elaborate in relation to EV chargers and their security considerations?
I think this is for Stephen.
Maybe, yeah.
I'll try to answer. I hope this smallest answer. So it's not that EV chargers are themselves dangerous. It's just that they make life more complicated for the distribution grid, and then you have to just cope with it. So that's the very short version.
Okay. How severe is this in real case? And then is there any educational courses? Are there any educational courses that you can suggest or provide?
Not really. I mean, at Holloway we have, as part of the master's program, we have 1-2 modules where we offer this, but these are not really offered for those not on the program. So it's not that we can filter that out at the moment. It might change, but at the moment, probably not.
Okay. Thank you. Yeah, you can also raise your hand and ask the question directly. Mohammed is asking about the presentation files. Yes, we will make this available on the INCSIOE website. Yes. Pramudia is asking for the same. We will do that. Chris Hankin is asking, do the CSSC test beds generate data sets that might be generally accessible in the same way that the test beds at SUTD in Singapore have been made available for cybersecurity researchers?
Yes, we can generate the dataset, but the usage is, I think the usage is limited to the member organizations of CSSC, because CSSC is based on the annual affairs of the organizations. So the kind of the priority would be for the member organizations, I think.
Okay. Thank you. More questions? Again, you can raise your hand or post it in the chat. Until we have a new question, I have to ask something, Stephen, please. So you mentioned, I think it was Siemens, a transition from Debian from proprietary software to Debian, right? And you weren't particularly happy about this. Now, there is this ongoing discussion with regards to open source and proprietary systems.
I mean, I'm not against open source, don't get me wrong, right?
No, I know.
It is really that all of these industrial control systems previously had the slight advantage that they were sufficiently obscure that an attacker would have to do extra work. Right? So I mean, Siemens is an example, Fabric, etc. But what has happened is that they've moved from essentially a completely proprietary architecture to what is now a transition to commodity hardware, where you're realizing some of the functions as VMs and you're simulating this. But that makes the underlying substrate, to my mind at least, more susceptible to these types of attacks. So it's about extending the attack surface. And I understand the cost pressure behind it, right? So that's the main reason, because you don't want to develop really specialized hardware in what are ultimately small numbers compared to the commodity hardware. And all major equipment vendors have exactly the same pressure. So it's not, I didn't want to single out Siemens, but it's really just as an example.
No, I know it was yeah, but I just wanted to ask you to highlight the attribute that you were targeting with this. Okay, thank you, Stephen. There is a question from Pedro. For pen testing, do you also develop custom exploit to explore certain vulnerabilities? And is there any proven vulnerabilities list that have been tested that we can view and learn publicly?
Yes, actually, we are trying explore certain vulnerability, of course, but our main objective is not actually not threat hunting or the unknown vulnerabilities hunting, but we are focusing on the kind of the breach and attack simulations, BAS things. So this is the kind of the another part of the penetration testing rather than the threat hunting or vulnerability hunting, to measure and evaluate the resilience things by the continuous monitoring and the evaluations.
Okay, thank you. There is a question from Rolando Martins. Hi, Rolando. I'm having issues with my setup. Nice present. Okay, sorry. From the UP side, we did some work with Coast, if I pronounce it correctly, on updates over the EV charging. For Stephen, will Gen AI, such as Mythos, will soon increase exponentially these issues?
Yeah. You're asking me to predict the future. That's always dangerous. But I think there is already an observable trend here, because a lot of these types of activities do not require sort of latest frontier models, but rather they're just applying existing knowledge that, well, particularly for industrial control systems, the system we're talking about here now, we were, until quite recently, protected by the obscurity of these protocols and systems. But we will share the slide set that we've used, and I have a couple of slides that I didn't present. But to give you one example, 10 years ago, the same group of Russian state-sponsored hackers had to manually intervene and did manual protocol unit tailoring to attack a system. They have since developed toolkits that allow somebody with limited technical knowledge to perform some of those attacks. And there's no reason to think that AI system will not play a similar role, that you no longer need to have, number one, that kind of obscure, detailed knowledge about protocols that nobody else even heard of. And number two, because a lot of the attacks that we're talking about here are actually requiring a fairly delicate sequencing in order to be really damaging. And that's exactly the kind of thing that automation systems like LLM models are great at. So I fully expect that this is going to have a negative impact. Whether it's going to be exponential, who knows? But it's definitely not helping.
Well, I think we had some news just today, actually, from the vice chair of the Senate Intelligence Committee, and they saying that the NSA chief told him that Mythos broke into almost all of our classified systems, not in weeks, but in hours. I just read this morning. So, there you go. It's not future, right? It's present, actually. We have a question from David.
Yes, good morning, good afternoon, good evening, everyone. So let me take us, and perhaps in a little bit of a different direction, but really directly home to universities. So this past spring, we had a ransomware attack on the Canvas education system that affected universities across the world. First question for the speakers is, should something like that really took down the education systems of the universities be considered critical infrastructure? And secondly, what would they recommend as easy and substantial fixes that could prevent that? And let's take off the table universities running redundant systems, because I think that's unaffordable for universities to be running simultaneously two systems. So I'd love to hear everybody's take on that.
Whoever wants to answer this, please feel free to.
I can start just quickly. Yeah, I think, of course, that's an infrastructure security issue. I will give you a different answer altogether from, I'll go to the basics. One thing that I recognized using Canvas, for example, is that we took those kind of systems for granted. So some of us, while we are teaching, were keeping the database of graded assignment and all of that on the system itself. So it's kind of like a no-brainer, but we haven't thought about it before, is to keep our own data stored in our own systems and not just depend on, not take things for granted, let me say it that way. That's the instruction that I gave my own teaching assistants and research assistants from that point on, to keep everything secured and additional copies stored elsewhere.
Thank you, Monty. Any other ideas?
Can I follow up on that question, on that answer though? Does that mean that there will be student proprietary information held locally on lots of different systems?
I think you have to have some backup information held separately, yes.
If I can follow up, so I think Canvas is just an example of an external service provider, because universities are contracting with an external provider, and that provider has an entire rat's tail of dependencies. I mean, the old joke is that in the end, you are depending on a DNS server run by Amazon somewhere on the East Coast, and the entire internet depends on that. And it's almost true. It's not just a joke. So we have a lot of these systems with cross dependencies that are not terribly robust, even without thinking about attacks. Now, you've asked, is it critical infrastructure? Well, the formal answer is legally it can't be, because it's not recognized in law by the whether it's in the US or elsewhere. So this sort of system does not have any special status or protection, but it is critical, of course, to the operation of universities, and then we just have to be able to cope with outages. And part of the problem with the Canvas outage was, of course, that we can't really know what information from students was potentially harvested and what the liabilities are that might be incurred there. I'm quite pessimistic, if you can hear.
Thank you. Okay, thank you, Stephen. We have one question from Kazuo and a couple of questions in the chat. Let's start with Kazuo, please.
Yeah, thank you, Konstantinos, and thank you for all the presenters today. So my question is about, these days I'm also involved in the AI, particularly agentic AI, automated, and how it is kind of dangerous, as well as utilizing well automated. For instance, Stephen, you mentioned a couple of standard IES, and like, for instance, 6 to 4.3, like automated, say, operations side to prevent, or somehow the fix, if you can, using AI. Are there any kind of practical cases that any of you are working on using detection or the fixing or preventing using those AI tools?
We're not using AI tools on our end. So right now, this is still very much a pencil and paper exercise. It might change in the future, but it's very, very much where we are right now. But it might have to change.
Indeed, it's already here now.
Yeah, if I can expand on that a little bit. So in our case, we are using AI to not only just to detect and respond to attacks, but also to try to encapsulate the actual behavior and find anomalies from that actual behavior and flag that as a potential attack. So in that sense, the AI is fundamental to this. But it's more importantly, we are embedding the domain knowledge into those AI models, and that's, I think, what could really be an important thing to do in all the work that everyone is doing.
Yeah, thank you.
Thank you. There is a question by Pramudia. The problem is how simulation can adapt to the vulnerability and, of course, predict the unknown vulnerabilities. The step is too complex. So how we can have adaptation to new vulnerabilities and or predict unknown ones with simulations?
Yeah. So I would say two things. The way that I look at it is two things. The first point is, if you have an existing system and you want to expose vulnerability in that system, then the simulation itself could be the way that you do it. So you are simulating the system, and you are simulating attacks, and you are simulating defenses. So it has a research aspect, it has education aspect as well. Then the other component of it is exploring the surface of the unknown. And for that, you will need the simulation. So you think of it as, again, like whether it's Monte Carlo simulation, whether it's looking at the complexity of the system by having different multi-agent systems interacting together to simulate a complex system. So there are certain things that you can only do if you are using simulation. Otherwise, you're not going to be explore that surface. And oftentimes, yes, the complexity might be high, but if you, again, are using the domain knowledge and embedding that in your simulation, and if you know the fundamentally how to simulate different components, then you can look at the overall behavior of the complex system as an outcome of that. And if you have any real data, then you can calibrate your simulation before you explore new things. So I think that's where everyone now is going. Simulation, modeling, domain knowledge, agentic AI, and reinforcement learning.
Okay, thank you, Monty. There is a question for Takao. Did you use open source BAS frameworks, or did you have to develop a custom solution internally? This is from Bambang.
Okay, thank you for the question. So the answer is the later. We are making a custom solution internally in the research team. So because we are focusing on the kind of the not only TCP/IP based network environment, but also considering OT protocols environment. So some of the protocol would be open source or standardized protocol, especially by IEC, for example. And the other part is not open or vendor specific or closed protocols. So it is necessary to consider such kind of the specific environment for all these things. to pass the actual traffic, and then so learning the protocol issues, the protocols, and then so realizing the continuous monitoring and evaluating the resilience issues at the environment.
Okay, thank you, Takao. Do we have any more questions? I don't see anything in the chat, and some people have to leave for other meetings. So I think we can wrap up. I would like to thank all 4 presenters for today's talks. This is great again, and I particularly think that the discussion at the end is quite useful and helpful. And I would like to thank everybody who participated and the extended the Inc. COE community. We are extending our community indeed, so we would like more experts to join us. So please be in touch with us. And from Inc. COE part, I would like to particularly thank Laura for organizing, setting up everything and making this happen in the first place. So we will have the next seminar coming up from September. So please stay tuned, and we will circulate information about the upcoming seminars. Thank you very much all for joining.
Thank you all.
For having us.
Thank you.